All right, so today's problem, this is day 22. We are looking at reorder linked list. And I've been saying this at the beginning of all the linked list problems, but just FYI, if you have not worked with linked lists much before, all they are is objects that point forward in a list. So in this case, we are working with singly linked lists. It's just an object that points at another object that points at another object, and it only goes forward in one direction. And yeah, okay. So here's the prompt. You are given the head of a singly linked list. The positions of a linked list of length 7, for example, can initially be represented as, and they give us this list. We won't actually be working with a list. This is just like a nice way to represent it, to tell us what to do. Okay, and so if we're given something like 0, 1, 2, 3, 4, 5, 6, our job is to reorder the nodes of the linked list to be in this new order, which is 0, 6, 1, 5, 2, 4, 3. And they give us a more general statement of that. They say in the general case for a list of length equals n, the nodes will be reordered to be in this new order, which is 0, followed by n minus 1, and then 1, followed by n minus 2, and then 2, followed by n minus 3. And so what they're trying to highlight here is that we kind of switch back and forth, picking from the front and the back of the list, and we move our way inward. So the first node and the last node, the second node and the second to last, the third node and the third to the last, and so on. Okay, and then another little note here. It says you may not modify the values in the list's nodes, but instead you must reorder the nodes themselves. So this fits on our general pattern of how to handle linked lists, which is that we'll just manipulate those next pointers to point to new places. So by rearranging those next pointers, we can sort of create a new list, or at least reorder the elements that are in the list rather than changing the values inside of those nodes. Okay, they gave us a pretty good example to start with, but here's another one. If we start with 2, 4, 6, 8, what we want that to turn into is 2, 8, 4, 6, and what that really means is make this guy point here, and make that guy point there, and then make this one point here. So we'll just, again, rearrange them. We're not actually going to move the values. We're not actually going to move the nodes. We're just going to make them point to different places. Okay, and then slightly longer example here for 2, 4, 6, 8, 10, which notice has an odd number. We have this guy points over here, points over there, points over there, points over there, and then we're done. And the last node will point to nothing, basically, to indicate that it's the end of the list. Okay, and then they tell us here that the length of the list will be between 1 and 1,000, whatever, we'll make do. And then the values, which we're not going to manipulate, but they'll be between 1 and 1,000. I don't think it gets mentioned here, but this is also going to, we're never going to have to deal with a list that has a cycle. So that's like an edge case that they don't mention that we won't have to deal with. So assume that it's just a bunch of nodes in a row that go forward, and then eventually we reach the end of the list. Okay, so as usual, one way that we can handle linked list problems is just to get them into a list in the first place, so like an actual array, and then manipulate it from there. So let's diagram this a little bit. One option, if we've got these nodes here, and I'll just call them like 0, 1, 2, 3, 4, 5 for ease of explanation here, but they could be anything. So if we had something like this, 0 points at 1, points at 2, points at 3, and maybe we'll go one more than that just so that we can have a more detailed explanation. Okay, so we could, if we wanted to, make an actual list and kind of go through this entire linked list and put these guys into an array so we can reference them by their index. So I'm going to just write this to indicate like we've put the node in there, or we have the address of it at least. Okay, so we can do this, and by doing this, what we get is like some additional context. We get some things like being able to randomly access the end of the list, for example, which we can't normally do. We're also able to like use pointers or indexes to move forward and backwards through the list, which is handy. Now, again, the weakness of this is we need extra space, right? So in this case, we need to have an additional piece of data for every node. And we will, after doing this approach, we will like try and handle this without needing extra space. But if we do it this way, then it becomes just a matter of playing with the indexes here. We'll have one that starts at the beginning and one that starts at the end. And we'll say, go ahead and make the first thing point at the last thing, and then go ahead and move it over. Now make the last thing point at the first thing, and then move that over. That's like kind of one step here. And we'll keep doing that. Make the first thing point at the last thing, move it over. Hello, move it over. Great. And then make the last thing point at the first thing, and move that over. Okay, and then once those two pointers hit each other, we can say, okay, we're done. Right, so you can see in this case we've got the thing we want. 0 points to 4, points to 1. So 0 points to 4, points to 1, points to 3, points to 2. And then the very last thing we'll need to do is make sure that 2 like doesn't point at anything. Again, we'll be able to detect this because the two pointers like have reached each other at this point. Okay, so yeah, that's pretty straightforward and definitely like familiar. We've done like lots of array problems before. And then just for the sake of completeness, let's also just run through this analogy if we have an even number of nodes. So we'll have like list nodes 0, 1, 2, and we'll just stop at 3 this time. Okay, so in this case, what'll happen is we'll have pointer at the beginning, pointer at the end. We'll do the same process, so make this guy, so make red point at blue, and then move red over. Now make blue point at red, and move blue over. Okay, and then we can make red point at blue, and move red over, and at this point, we want to stop, right? So because we're kind of doing this in 2 motions at a time, so to speak, we're going to want to check in the middle, like, hey, have they actually already hit each other? If they already have hit each other, then let's just stop, basically. So yeah, there's like kind of that one additional case that we need to check for, which is totally fine. It's pretty easy to do that in code. And again, our like stop condition, if we decide to use extra space like this, is just, hey, the 2 pointers are the same. In that case, we're done. We've already connected everything we need to connect, and we can go ahead and just like cut off the list and call it a day. Okay, so let's see if we can, I've actually never coded up the extra space version because I like learned this, I think when I like did this problem at first, I just thought I kind of stumbled on the optimal solution pretty early. So let's see if we can do this. We'll say we need a current pointer that points to the head at first, so we'll initialize this first. And then we need a list, which I'll call like node list here, which will be empty at first. And then as long as we have a node to point at, we're gonna kind of populate node list here. So node list dot append is what we'll do here, current, and then move current on to the next part. And then hello, if you just hopped in, we are doing the extra space version of the solution first, and then we'll go on to the optimal solution. Great. Okay, so this is going to hopefully give us the complete list of nodes. We'll just real quick check if we have that. Now, one of the problems here is if I print like the node list, what it's actually going to print is a list of addresses because these are objects, right? So instead, here's what I'll do is I'll print node.val for node in node list. So this is just to verify that we have everything we need. Let's give it a run. And this prints out 2468, which is exactly what we want. Okay, so we got all the nodes, which is great. What are we gonna do with them? Again, we're gonna follow this pattern of like point to the back, move, so like red points to blue, move red over, blue points to red, move blue over. Okay, so here's what we'll say is, well, there's actually a few ways we can check this. I was gonna say while red, left does not equal right. And I guess we kind of can do that. Speaking of which, we'll have to initialize these to 0 and length of node list -1. Okay, so they start at both ends, and we're gonna say as long as they are not the same as each other. I almost think though, well, okay, let's type it up and then we'll make some changes. So as long as they don't equal each other, what are we going to do? We're going to say node list left dot next equals node list right. And we don't need to worry about losing what was originally in the next position because we have them in an array, right? So the extra space means we don't have to like concern ourselves too much about where the pointers are pointing or like losing data. So we'll make left point to right, and then we'll move left over. Okay, and then here's the extra thing. Remember, when we have an even number of nodes, like halfway through that process, the red will hit the blue. So we should actually check at this point, like if the red is the same as the blue, we can break. Okay. Yeah. Now, this leads me to what I was going to say earlier, which is it might actually be a little bit nicer to say, like, let's go ahead and let this run forever. Just in these two places, though, we're going to check if left and right are the same. I think this is a little bit more expressive of what we're actually trying to do, because this kind of suggests, like, if we put it up here, like, oh, we should get through this every time. That's not super true, so instead we can just say, check at the beginning and also check halfway through, right? So I like that a little bit better. I think you could probably argue it either way, but after we make the left point at the right, we move the left over, and now we're going to make the right point at the left. And we've already guaranteed at this point that they're not the same as each other, and then right will move in by 1. Okay, so eventually we get to the end of this. They're going to be at the same place. Now the last thing we have to do is disconnect that, like, the final node. So we're going to say something like node list right dot next equals none. And then what are we going to return? We can actually just return head, because whatever was originally at the front is still going to be at the front. Okay. Now, the only case that I can think of that's going to break this is if there's no nodes, but we're actually told that there will be at least one node. So I think we're set to go here. So let's just make sure this actually works, because again, I've actually never done it this way. Ooh. Oh, I need to return. Nope, I don't need to return head, because we're modifying it in place. Great. Okay, so this does work, but again, the weakness here is it requires extra space, right? We have to record all of the nodes, which is potentially, 1,000 extra nodes of information that we have to store. And then if we do that, the trade-off is it's very easy to like reference other things in the list. We don't have to worry about like dangling pointers. But if this was an interview, they'd say, okay, you did that with extra space. Could we do it with no extra space, right? And if you think about what we did here, I'm going to do a little bit of erasing. The overall approach, and if you look at like the general case up here, this whole like 0, n minus 1, 1, n minus 2, 2, n minus 3, if you kind of track these on each side, you'll notice that like half of it is 0, 1, 2, 3, 4, 5, right? It's kind of tracking from the front to the back. And then the other half, n minus 1, n minus 2, n minus 3, this is tracking from the back to the front. Right, and so we can actually do basically exactly that. We can just take these nodes, split them right down the middle, and basically just go like from here through here, and then from here through here, taking one at a time. And if we can do that, we'll have the same effect as what we had before. It's just we don't need to record the nodes anywhere. We can just have pointers that walk from the front to the back and the back to the front, respectively. Okay, so how do we do that? Well, we're going to need to find the middle of the list is the first thing. And I'm saying middle a little bit roughly because what we really want is kind of what's right after the middle. Or if it's an even number of nodes, then you're still like right at the middle. And then what we'll do is we'll need some way to get through the back half of the list in reverse, right? Since it's a singly linked list, it originally only goes forward, but if you were here a few days ago, we did reverse linked lists, so we also know how to turn lists kind of backwards. So yeah, and then once we do that, we'll just need some mechanism for like picking from the back and the front in succession, or the front and the back in succession. which can be very similar to what we just did, just without the indexes. So that's the overall strategy, and if we do it that way, we don't have to record the nodes anywhere. We can just have exactly two pointers that travel the front half and travel the back half, and then we're set to go. So yeah, that's actually kind of it. And then I guess the extra note here is we will want to actually sever this connection right here, because we don't want the red pointer to like continue to the back half of the list, right? So we'll actually separate into two lists, reverse the second half, and then make them like point at each other. All right, let's see if we can do that. And also I'm like sort of blazing through this just because we went through two approaches, but if anybody has questions, please let me know. Very open to questions. But let's take a look. So I'm actually going to outline this in comments, which I think is a really good practice in general. I don't often do this because like I'm literally explaining it as I talk, but I think this is good practice. So step one, find the midpoint of the list. Step two, we will reverse the second half. And then step three, we'll like interlink the halves. Okay, so how do we find the midpoint of the list? Well, we actually saw this problem. Did we? Wait. Did we do midpoint? Hold on. We used an algorithm that is related to this. We used fast pointer, slow pointer, or tortoise and the hare yesterday for figuring out if there was a cycle. The other kind of benefit of that algorithm is it'll let us find the midpoint of the list, because if we have a pointer that travels 2 nodes every time and a pointer that travels 1 node every time, then by the time the second pointer gets to the end, the first pointer will be halfway through. Oh, helicopter. I'm gonna let the helicopter pass real quick. Helicopter. Okay. That's my Lambo at the mechanic. Okay, sure. Okay, so how do we find the midpoint of the list? Let's think about this. Yesterday I said we have slow and fast that will both point at the head initially, so we can say slow equals fast equals head. And then I think the while condition was while fast.next and fast.next.next. And this is saying like as long as there is actually both a next node and a next node, so that you can travel 2. Is essentially what this means. Okay, so what are we going to do? We're going to say slow equals slow.next, and then fast equals fast.next.next. Okay, and then, yeah, I guess there's an extra step in here that I forgot to mention, which is, again, we'll sever the first half. Okay, now the only thing I'm a little bit worried about here is, and I always forget how this ends up, we want if there's like an odd number of nodes, we want the extra node to end up on the first half. So let's just make sure that this actually does that. We'll say at this point, let's go ahead and print slow.val, and also, no, actually that's it, huh? We just need to know if we're getting the right one. So let me go ahead and print that real quick, and let's see what happens. So right now we have 4, which makes sense. That is the end of the first list. And then for this one, we should get 6. Okay, yeah, so we do, like in this one, we have 5 nodes, and the first half ends right here, is the idea. Okay, so we want that guy to point to none so that we can like sever the first half. But we also need, okay, so God, there's a lot going on here. So we need to say something like slow. Okay, let me rename these actually. Well, no, okay, we won't rename them yet. Slow is currently the end of the first half. Okay, so we'll say slow.next equals none, but the problem is slow.next is also the beginning of the second half, right? So we'll also say like, I'll say reverse. Oh, no. Second head? Second head equals slow.next. There's a joke in there. Yeah. This is like the hobbits, you know, when they're like second breakfast and like second head. Okay, I'm sorry. I can't believe that's gonna be in the recording. Kill me. Okay. Slow.next is none. Okay, so this does two things. First of all, it gets us where the second half of the list starts. And it also gets us to cut off like what comes after the end of the first half. Okay, so we accomplished two things there. Okay, so now we need to reverse the second half, and this is another problem that we've done before. So if you don't know how to do this, pause the video, go back to reverse linked list, and you can learn that part. But I'll just go through how to do it here in terms of the code. We'll need a previous and a current. Previous starts as none, current starts as the second head. And then we'll say while cur, I think, will cur. So as long as we're pointing at an actual node, what are we going to do? We'll say we need a temporary variable to store the next thing in the sequence. So next node is going to be cur.next. And then cur needs to point backwards. So now cur.next equals prev. And we initialize this to none because the very first node is just going to point backwards at nothing. And then whatever was current right now, it becomes previous. And then whatever was next to be processed becomes cur. Okay. I think that's it. And then at this point, we've reversed the list, and we also have a pointer that points to the head of the reversed list. So I'll say rev head equals prev. Okay, so we exit this loop right here when current hits the void after the last node. And at that point, cur is pointing at nothing, prev is pointing at the previous end of the list, which is now the head of the reversed list. Okay, lots going on there, but that should work. And then again, just for diagnosis here to make sure we don't move on with faulty data, I'll go ahead and print revhead.value. And in fact, what we could even do is we could traverse that whole... Yeah, you know what? Let's do a little bit more diagnosis just to make sure everything's working here. I'll say like cur equals head. And then while cur, print cur.val, and cur equals cur.next. Okay, so this should print the front half of the list. And then let's also print the back half of the list. Which is reversed. Okay, that, and then... Okay, let's just make sure that all works, and then we'll do the interlinking part. Oh. Okay, there we go. So we got 2, 4, and 8, 6. That's exactly what we wanted. Here we got we should get 2, 4, 6, and then 10, 8, and that's exactly what we got. Okay, sweet. So the lists are as we hope for them to be. I'm gonna go ahead and delete this because it worked, but maybe in a different world we would have commented it out. Okay, and our final job here is to interlink the halves. There's actually a few ways to do this. And if you were, I actually interviewed someone at mock interview night who had like a really, I think, a nice approach. Historically, I've done it the way we talked about earlier, where I think of the interlinking as like front to back, back to front. That's like one iteration of the loop, so to speak. But I actually liked this approach a little bit better last time, so we'll do it this way. We'll say, I'll create a Boolean variable that I'm going to call should pick from front, I'll say, like pick from the front half. And when we start, we do want to do that, right? We want to pick from the front half. And then, oh boy, let me think about what the loop condition should be here. We need like a tracker on the front half and a tracker on the back half, because we need to like actually traverse the front half and traverse the back half. So I'll say like, well, front and back. These are going to be head and rev head. Okay. And let me think about this real quick. Okay, so we know that they're either the two halves are the same size, or we have an extra one on the front. So when should we stop? We should stop when the front hits like none, right? So I'll say while front. Is that right? Ugh. Okay, let's think about this. So if we have an odd number, then we'll have like connect to the front, connect to the back, connect to the front, connect to the back, connect to the front. Hold on. No. I've got the order of that wrong. In terms of the loop, what's going to happen is we connect here, and then we move it over. Connect here, and then move it over. Connect here, then move it over. Connect here, and then move it over. Connect here, and then move it over. But we've severed them, so this is going to go to nothing. So yeah, I think the condition is correct here. We'll say while front, and then the other thing we need is something that will like follow the entire list instead of just the front or the back. So I'll say we'll have like and this is another strategy we've explored before, so if you're like, what the heck does dummy head mean? Go back to one of the previous days, because we talked about it. So we're gonna have this like fake node. I guess it doesn't matter if it's this actually, because we know that the first node is gonna be... No, actually, wait. We're doing this in place. So anyways, it doesn't matter where this is. We can actually kind of point it anywhere. But I'm going to do this just so that like it sort of works out elegantly. I think. Hold on. No, we don't need a dummy head because we're just going to return head at the end, or like head is modified in place. So I think we can just have like a traveler node. Oh, does it matter? It doesn't really matter. I'm just going to say this just so that when we connect the front, it just like kind of works out properly. Okay. So I'll say while front, and then right here, if we should pick from the front, then what's going to happen? Let me give myself a little bit more space here. If we should pick from the front, what will happen? We'll say traveler.next equals front. And then front moves forward, right? Front equals front.next. Okay, otherwise, traveler.next will be whatever's in the back, and then back will also move, quote unquote, forward. It'll move like inward, so to speak. Okay, and then either way, now we need traveler to go to whatever it got hooked up to. And then we also need to say, let's not, if we picked from the front last time, let's not do it again. So we can say should pick from front equals not should pick from front. Okay, and again, whatever was on the end of the first half was already pointing to none, so we don't need to manually do that this time. It's always going to be the last thing that we pick, I think. Oh boy. Yeah, both of the ends actually point to nothing. So wherever we stop, it's already pointing to nothing, and it is the end of the list, and we're good on that. So I think this is it. So all this is doing is it's saying whatever node we're currently on, if it's the front's turn, hook it up to the front, and then move that pointer over. But if not, it's the back's turn, hook it up to the back, and have the back move to the next node. Either way, Traveler goes on to the next part of the completed list, and then we swap the next time around. Okay, is that it? I guess we'll find out. Let's take a look. No! Okay, let's take a look. 2840. Oh, I think that it might be this condition because we just left off. Yeah, this one completely does it. So I think, if it's an even number, then the front actually gets to the end and we never hook up the back. So I guess, well, front or back? Because that way, if it's the back's turn and there's something there, we should hook it up, right? Okay, I think that'll do it. Let's see. Great. Oh, no, I don't want to copy it. I just want to see if it finishes. And it does. Yippee. Okay, so yeah, this is, honestly, I've never done it this way before, but I kind of like it. I think it illustrates like the goal of picking from the front and the back really well. It's a little bit tricky to set up, but yeah. And I think this right here, like this whole like figuring out all the tiny edge cases and the odd or the even, I would really say, like, if you can't figure it out, just write it out, you know, like type up an example and try it and see if that condition needs to be changed, you know. This is pretty fresh on my brain because I did it pretty recently as part of the mock interview nights. But definitely, like, while I was asking these questions for the interviews, it was very much like, oh, let's just do an example to see how it works, instead of just like theorizing it out, because that can be very confusing, especially with linked lists. So yeah, but I thought this was cool. I like this approach. I'll probably use it if I get asked this question in the future. And that's that. Okay, and yeah, I tend to not do this again, but I really highly recommend it. I think this is a good practice to be in. Like, pseudocode the structure of your solution. This is great, just so that you can break it down and you know what each step is supposed to do. You can even, like, you know, in the vein of like doing things that are good in production code, like this whole idea of like unit testing almost to make sure that this does the thing it's supposed to do is, like, I think a very good skill to demonstrate. Obviously we've deleted all of it because we don't need it by the time we're done, but that can be a good thing to demonstrate, that you like understand good testing processes, right? Anyways, that wasn't too bad. Given that we did 2 solutions, 35 minutes, I feel good about that. Any questions at all that I can answer right now? And if not, think of the questions. I will answer them later happily and joyfully. Oh, someone typing. Someone typing. Speak your mind, Marshmallow Dog. Oh, so the way that I usually do it is kind of what we did in the extra space solution, which is this one. So it's obviously not going to look exactly the same, but usually the way I think about it is like that one iteration of the loop hooks the front up to the back and then the back up to the front. Like, I think of that as one iteration, and then I'll just check halfway through if we're done, basically. So check at the front, check in the middle. It's effectively the same logic, we just can't use the indexes in this case. Like, we would just have separate pointers for the front and the back as we do in the final version of the code, and then the loop structure just looks more like this. And another weakness of this is this means we have to manually set something to, well, actually no, we don't in this case, but yeah, this would be the other approach, just not using indexes. Instead, we would just use those front and back pointers here. I think they're like roughly the same in terms of like how elegant they are, I suppose, but I think this one captures the thought of like what we're doing a little bit better, because it's not forcibly saying like one iteration has to be the front to the back and the back to the front. This is just saying like just pick from either end and alternate, and I like that about this approach. So yeah, and I guess again in the vein of like what should you do during an interview, I think the method that best captures your thought process or what you want to communicate in the code is the one you should go with, unless it's like especially non-performant. So this one, it takes a little bit of extra like code to set things up, but it, I think, very clearly captures the intent, and I think that's important, and your interviewer wants to see that you're good at capturing intent like that. Sweet. Great. Well, thanks for tuning in, chat, and we will not be back to it tomorrow because it's Friday, and I hope you enjoy your weekend. I'm going to be at a little Halloween gathering, and I think I'm going to go as... I think I'm going to be one of the robbers of the Louvre from this last week. I'm going to, like, get a ski mask and a black bodysuit and, like, carry, like, jewels and maybe a copy of the Mona Lisa. Yeah, a crown. Yeah, it feels timely. And also easy to put together, which is really important for me. Anyways, have a great weekend, y'all, and we'll be back to it with more linked lists next week. I can't remember what. Remove nth node, that's a pretty easy one, and then merge k-sorted lists, which is our second hard. And then also next Tuesday, we have a general body meeting where we're going to talk about stacks and binary search and linked list and do some practice. So if you want to come through, it'll be Tuesday night. Okay, that's truly all I have to say now, so I'll let y'all go. But have a good weekend. I'll see y'all next week.